All right, our goal now was to introduce two other kinds of potential energy functions, one for systems involving a spring force between two parts of the system that will be considered an internal force, and one is for systems where masses maybe are separated by large distances like the moon and the earth, or if I'm dropping an object from far, far above the moon and letting it fall a huge distance, I can't use the force equal to mg that we used in deriving this one. So let's see how we get the potential energy functions associated with those. First, the spring force, and we need to learn a little bit about the spring force, and in this case we're going to call the spring force law Hooke's law, but let's think about it for a second. Imagine that this spring in the middle here is completely relaxed, and I don't want to think about any forces acting on this mass m except the spring force. So let's imagine we're in outer space. This is the side of my spaceship here, a really massive spaceship, and here I've got a spring connected to a mass, but I've let the spring totally relax, so it's not under compression or tension or anything right now. Okay, and what we're going to do is pick a location on the mass. I will choose its left edge, and what we're going to do is mark its location on an x-axis over here. And we're always, when we're considering springs, draw the positive x-axis in the direction that would stretch the spring. So in this case, plus x is to the right in my diagram. And when we have a relaxed spring, the other thing we have to do is wherever we're going to use to measure positions of the mass, I've chosen the left edge of the mass, on our x-axis, by definition, that relaxed spring is going to have a position of the mass, or whatever it's connected to, of 0 on the x-axis. So the mass at x equals 0 means the spring force is not exerting any force whatsoever. Now let's imagine we take that spring and I pull it with my hand in this direction, so it's now stretched, as in the upper figure right here. The spring force, of course, if I'm pulling it to the right, the spring force is going to be pulling it back to the left in that case. So I'm going to imagine I've stretched it out so the left edge of the mass is at some x coordinate x on the x-axis. And the force law that tells how big of a force that the spring pulls back on the object with is given by this. The x component of the spring force is equal to minus a constant times x. In other words, the bigger x is, the larger the spring force is that it pulls back. That kind of hopefully agrees with your intuition about a spring. Okay, that force law, Fx is equal to minus kx, is called Hooke's law, after the original inventor of that mathematical model of springs. That constant k is called the spring constant for the spring, and it's particular to the type of spring that you have. The units for the spring constant k are newtons per meter. You can see that just by solving for k up here. We would have a force divided by a distance x. And the physical significance of k is that a small k corresponds to a very weak spring that hardly pulls at all. Maybe the coils are very thin wire. And a large k would correspond to a very stiff spring that would correspond to really thick turns of metal in here, something that's really hard to stretch and really hard to compress. Okay, so that's the spring constant, and it goes in Hooke's law, Fx equals minus kx. Similarly, let's imagine if we compress the spring, as in this third image down here. So here I've taken my hand and I've pushed the spring in maybe to some other negative x value down here on the x-axis. The spring force would now be pushing outward. And I guess I should have said in this previous case up here, the minus sign corresponds to the fact that if I've pulled this mass out to a positive x, the x component of the spring force is negative, which agrees with the fact that it's pulling in the negative x direction. Remember, positive x is in this stretched location. Similarly, if I compress it in, the spring force is pushing in the positive x direction, which means this side should be positive. It looks negative, but it actually is positive because now we've pushed it into a negative x location. So the minus sign in the x combined with the minus sign out in front give a positive spring force x component, which agrees with that picture over there too. Now, the whole point in this was to get the potential energy function associated with this. The book, I think, shows how to do it with a geometric argument, but it's a little bit complicated because as I stretch this from maybe x equals 0 to some other x value, the spring force isn't constant, so we can't use our old formula for the work that involved a constant force. It's getting bigger and bigger as I stretch it to a larger x value. But in any case, there is a way using the areas under the curve argument to get the work done by the spring force as you stretch it to position x, and the associated potential energy associated with the spring internal force is equal to 1/2 kx squared. So what that means is if I stretch the spring, I put more and more potential energy into the spring, which could be converted to kinetic energy if I let it go. And if I compress the spring, that's a negative x. Notice when I square it, it doesn't care if x is negative or positive. The squaring it just gets rid of the minus sign. So I also put positive potential energy into it when I compress the spring, because if I let go of the mass, it would be converted into kinetic energy. So let's put that in our list of things down here. If we've got an internal spring force between two masses in our system, the potential energy associated with that spring force is 1/2 kx squared. And here the assumption is that plus x is in the direction of the stretch, although that doesn't really matter for us here because the x is being squared in any case. Finally, I'm not going to derive this expression either, and it does not appear in the book, but we're going to do some problems associated with it, so you should know how to use it. You don't need to know where it comes from. If we've got two spherical masses like the moon and the earth, and we're considering the gravitational force between them to be an internal force, then there's a potential energy associated with that gravitational force. And we can't use this simpler formula here because the object is not necessarily close to the surface of the Earth, or we might not even be talking about the Earth anyways. And so here the associated potential energy is sort of a peculiar, it's related to that Gm1m2 over r squared. But notice in this potential energy thing, this formula, the r is not squared in the denominator, and it's got this additional minus sign out in front. And you might think, well, that's kind of strange. How do I think about the minus sign? And the answer is, well, let's think about our intuition that we're developing now, that if I push the book up near the surface of the Earth, in other words, if I increase the separation between my book and the Earth, I'm increasing the potential energy in the book-Earth system due to that internal gravitational force. It's the same way with this formula, although it's a little bit confusing to think about. Let's plot that formula for, I'm going to imagine an object M, maybe that's the moon's mass, and here is the Earth's mass, and they're separated by a distance r. The distance between the center of the moon and the center of the Earth is r. And let's graph what this formula looks like as a function of r. R, of course, is always positive, so this formula is always negative. It never becomes positive when we're using it. But if we graph that negative function, it looks like this. It becomes more and more negative as r becomes smaller, and then as r becomes larger, when you divide by a larger number, it becomes smaller and smaller. So it becomes a smaller and smaller negative number. And notice that at least it makes sense in the sense that as you increase the distance between the moon and the Earth, the potential energy is getting bigger and bigger and bigger. It's going up and up and up on the potential energy axis. So it seems to be doing the right thing. The minus sign is sort of a pain. We just got to keep track of it and not worry about it too much, and it will give us the right answers when we show how to use that work-energy relationship. So here's our list of potential energies. These are the only three we're going to use in this class, and now our job is to show how we use those in the context of problem solving.